Hi kids. I thought it would be helpful to record a little Unit 2 review. So if you are interested, take out a blank piece of loose leaf and fold it lengthwise. And then separate it into these four categories. So on the outside of the paper, over here, you're going to fold a loose leaf for Dalton, Thomson, Rutherford, and Bohr. Those are the four scientists that are going to be asked about on the regions. You should also know Democritus and Heisenberg Schrodinger are both before Dalton, and Heisenberg Schrodinger are after Bohr. But these are the four that will be asked about on the regions. So go ahead and do that. And then open up your loose leaf, back up, and on the left side, go ahead and write models on the top. I didn't put the margin here, but go ahead and put model, and then on the right side, put conclusion. So model, you can either put notes or you can draw a picture. You should probably do both, and then conclusions. So go ahead and try and do that from memory now, and pause the video and see how much you can get done. All right, so you hit play again, you're back, you have this all filled in. So I'm going to go over it now. Go ahead and check your answers, whatever you don't have filled in, make sure that you get filled in. All right, so Dalton, the model is the billiard ball model. It is a hard sphere. Conclusions from Dalton are that atoms are indivisible. We now know that that is incorrect. Atoms we can actually break apart into their positive and negatively charged subatomic particles. So that's why I put this little star there. But that was the conclusion that Dalton came to. And he said that the identity does not change when they go through a chemical reaction. So, for example, this morning I had cornflakes for breakfast. There was glucose in my food. That was my fuel. My body broke it down and changed the C6H12O6 in those sugar molecules into carbon dioxide and water. Right now, as I'm speaking, I'm exhaling carbon dioxide and water, and that same carbon, potentially, that I ate this morning that was in the glucose molecule, that same exact atom has been rearranged into a new compound of carbon dioxide, and I'm exhaling it as I speak to you. So that's the main conclusion of Dalton is nothing can be created or destroyed. Everything is just rearranging, and you can think of all of those particle diagrams falling under the Dalton theory umbrella. All right, then came along was Thomson. Thomson ran experiments with cathode ray tubes and saw that that you could polarize a neutral object, and he hypothesized that atoms looked like plum pudding. Electrons were negative particles, and you had the same number of positively charged protons, but he thought there was a uniform distribution of protons and electrons, and I put that little star there because we know that that is the part that we now know is incorrect. We now know that that is not true. Hold on one second. All right, back on this screen. This is a recap of our proof that atoms are in fact made up of the same number of positively and negatively charged objects. Remember, this is our sticky tape. The bottom tape has the positively charged protons. The top tape as well has the positively charged protons that are, when we now know, trapped in the nucleus. But at the time, J.J. Thomson did not know that. He was able to polarize a beam of energized atoms based on the idea that we could have adding negatives to one side would make it more negative, and taking those negatively charged particles away would make a positively charged substance. So the way in which the tapes became charged is that the negative electrons moved from the top tape to the bottom tape. That excess of negative charge is why this has a net negative, And the lack of negative charge is what gives the top tape the positive, because remember that protons are trapped in the nucleus and only electrons can move. All right, I'm going to go back to going over your foldable there. Next up is Ernest Rutherford with the nuclear model. Remember, he ran the gold foil experiment and he came to 3 different conclusions. Atoms are mostly empty space. That is because alpha particles mostly went straight through the gold foil. There's a small dense nucleus. Small means that it has a small volume. Dense means it has all of the mass of the atom contained in the nucleus. And remember, we have those nucleons, protons, and neutrons in the nucleus there, where we have all of the negative charge, and electrons exist surrounding the nucleus. Many of you on your history projects had orbitals for Rutherford. Rutherford doesn't have orbitals, so he just thought that all of the electrons were like moving around randomly outside of the nucleus. All right, then we get to Niels Bohr. Niels Bohr had the bright line spectrum and the flame test, and he has the planetary model. He coined the term orbitals, and he said that electrons exist at distinct distances from the nucleus, and he concluded that based off of the bright line spectrum experiment. And so you should have orbitals here. You could have drawn electrons in there, but we call that the planetary model, and that's why we call those distances orbitals. A little more on Bohr. I know, very corny. Anyway, here is the diagram with those orbitals. Remember that the electron configuration tells us where the electrons are within the atom, how they are oriented. The ground state is the regular configuration where electrons are in the lowest possible orbital that they can possibly be in, so the lowest energy level. The excited state is when they jump up. And the bright line spectra is the series of bands that are given off. So here would be hydrogen, heated up very high. These were those glasses that we wore, but there's a prism. And this would be hydrogen's series, banding series, so a short drop and then larger drops would be indicated like this. And remember that the bright line spectrum can be used to identify the element, because the spectrum will be the same no matter where that atom is. Just like Dalton said that an atom of hydrogen on Earth is going to be the same as an atom of hydrogen in space, because all of them are identical to each other, at least in terms of the electronic structure, due to the number of protons in the nucleus determining the banding pattern of those electrons. So just a little recap on those scientists. Recap on subatomic particles. We know that J.J. Thomson correctly identified the electron as a negatively charged subatomic particle that's outside of the nucleus. We know that it is outside of the nucleus based on Rutherford's experiment, which also pointed out that all of the protons were positively charged and they were also located in the nucleus. Actually, Chadwick, you do not need to know his name. He actually figured out that neutrons were this other third mysterious particle that have mass but no charge. So here's just a little diagram where you can see the protons have a positive 1 charge and they have a mass of 1 AMU, which we're going to abbreviate just with a U now. Neutrons have a charge of 0 and they have a mass of 1 AMU, so that's shown here by this size representation. Electrons are teeny weenies, so they have basically no mass, but they do have a charge of -1. So there's that little recap of subatomic particles. Another little, here you go, remember this chart. In terms of subatomic particles, remember the locations of electrons in the orbitals and protons and neutrons in the nucleus, as well as these shorthand notations for those particles. So if you need to recopy this chart, don't forget that that exists. And we set 1.67 times 10 to the -24th grams equal to 1 atomic mass unit, or 1/12 of a carbon-12 atom. Isotopes, remember, have the same number of protons, different number of neutrons. Another way to say that is the same atomic number and a different mass number. Just a reminder that we name isotopes by their mass. So this isotope would be hydrogen 1, hydrogen 2, hydrogen 3. So that dash notation, just remember that that notation exists. And the more common isotopic notation, so nuclide, elemental, isotopic notation, you need to know that those are pretty much synonymous for each other in these terms. And we call the number on top the superscript and the number down below the subscript. So just a reminder, and then X right there represents the symbol. So you definitely need to know this. And just a reminder of the key here that tells you that it's relative to 1/12 of a carbon 12, 1 AMU there. Just a reminder that the atomic mass is actually the average atomic mass, and that's a special kind called the weighted average. And it's due to the relative abundance in naturally occurring isotopes. So that's definitional. And here's an example of a practice problem that you might encounter. So just walking you through it, that there are two isotopes of boron, and these are the three ways that you might note that isotope of boron 10. And here is an example of how you would work out that math to come out to 10.8. And so in general, you're going to do the mass times the abundance plus the mass times the abundance, and so on for however many isotopes you have for that particular element divided by 100. I taught all of you guys to use the decimal percent instead of this fraction notation because I think that at your math level, that's just more conducive to where you're at. So if you need to have another practice problem, here is another Regents example. And once you can pause the video and copy it down, try it out, and then once you calculate it out, you should get the value that is on your reference tables. If you pause the video, I'm going to tell you the answers in 1 second. All right, so in terms of atomic particle state one difference, the same number of protons, a different number of neutrons. The atomic mass should be this value times the decimal percent here, or these two values multiplied by each other, plus these two values multiplied by each other, plus these two values multiplied by each other, all divided by 100. This sometimes confuses kids because when you move the decimal 2 times for a decimal percent, that sometimes trips kids up. So if you would prefer to do it as the fraction notation, that's cool too. And the last one, it's going to be closest to neon 20 because there's 90%. So that tells you that that is going to be the closest whole number, right? All right, so electron configuration, I just wanted to show you and remind you that the Regents is like the Quickville version for carbon 2,4 for those 6 electrons. So just to remind you, there's the Bohr model, there's the isotopic notation, and there is the electron configuration here. So the excited state electron configuration, this was for aluminum. If the ground state for this example is 283 for the 13 in that Bohr model where there's 2 electrons in the first, and then 8 electrons and then 3. One example could be 2821 where 1 electron moves from the 3rd orbital up to a 4th orbital, but any way in which either an electron from the 1st orbital or the 2nd orbital moves to the 3rd. So the most common would be 274 for this example, but this was just another example. And if you need to know the definitions for either valence electrons or the core electrons, which also old school used to be called kernel electrons, those are right there for you. Atoms can become ions by either losing electrons or gaining electrons. So this is what we did the last day of the unit. And just a reminder that when an atom loses electrons, it becomes a positive ion, and its radius becomes smaller. It has lost an entire orbital in this top example, which is what this was from. And then remember that when an atom becomes an ion that has a negative charge, it's actually gaining an electron, which is why I crossed that out and put that there. And in this, the atom is going to be larger I mean, the ion is going to be larger than the atom because it gained an electron. So that's what is noted here. So in general, anytime an ion is formed by losing electrons, the radius is going to be smaller. And anytime an ion is formed by gaining electrons, the radius is going to be larger. So positive ions are smaller in radius than the atoms in which they came from, and negative ions are larger in radius. And so that's a little bit to get used to because it seems kind of backwards. But losing electrons gives a positive ion, and metals tend to do that. Non-metals tend to gain electrons. And remember, this has to do with getting to 8 electrons. Aluminum loses 3 and then ends up with 8 below in its second orbital. And notice that chlorine is going to just gain 1 and end up with 8 in its valence orbital. So that octet rule is at play here. All right, so now I'm going to do the honors material, the stuff that's beyond the scope of just the Regents exam. So if you're watching this as a Regents review, go ahead and stop. But if you're watching this for the unit test honors review, keep going because this is going to be on there. So Heisenberg proposed that Bohr wasn't exactly right, that the electrons were moving actually in a wave pattern, and he called that the uncertainty principle. He basically said that you can't tell the momentum and the location of an electron simultaneously because electrons move in such random patterns that we can do one or the other at a time. He also changed the name of an orbital to a level, but we're still going to use orbital, level, and shell interchangeably. Schrodinger redefined orbital as a region of most probable location, meaning that we have a high probability of finding mathematically the electron in a region. However, knowing exactly where it is, we still can't do. So that's what Schrodinger figured out. And Schrodinger tried to explain this in the most confusing way possible, using the Schrodinger's cat idea that the cat is both dead and alive, and using this radioactive decay model, which would be metered in a certain understandable way, which is what he was trying to get at. But being the brainiac that he was, had a hard time conveying that. So remember, think of Schrodinger's phone. The phone is both broken and it is not broken at the same time. But the main thing here is that we developed what's called the wave mechanical model. You need to know that this is the most modern model of the atom that we have. And electrons act as both light and particles, and that is called the wave-particle duality of electrons. What cool guys. All right. All right, so we know now because of Heisenberg and Schrodinger, that the energy levels actually look more like this. So here's our Bohr model. Here is our Heisenberg-Schrodinger splitting model. And you should review this chart. It will be on your test, replicating it. So there's a little tip if you got this far into the video. Remember that the periodic table is set up very specifically. You should be able to use the countercross method in order to do an electron configuration in SPDF or sub-level format. So make sure that you review how to do this. And the energy level diagram, you will have to be able to replicate as well. So know that the S has 1 sublevel, and the P has 3, and the D has 5, and the F has 7 for a max of 14 electrons. And so you need to know upspin, downspin notation, as well as Aufbau and Hund's rule. All right, so make sure that you know and are proficient at filling in those upspin, downspin vector arrows for the electrons. And that is it. So the electron configuration sublevel, the level, sublevel, and the number of electrons that appear in that sublevel. All right, so that is your Unit 1 review in under 20 minutes, so that's pretty good. All right, if you have any questions, email as always, and hopefully you are doing some practice problems in order to review. All right.